Hi everybody, this is lecture 23 and today we will talk about flux. So, you, so we'll talk about flux and maybe if there's time at the end I'll tell you about the divergence theorem. This is a very beautiful theorem. It's due to Gauss, so that should tell you that it's deep stuff, good stuff. And so that's my plan. All right, so let's get started. So here I have a little surface and a vector field, and we're going to be talking about how much this vector field flows across the surface. The flux is going to be this number, right? It's going to the number is going to have a sign according to whether the flux is in one direction through the surface or in the other. Maybe this as opposed to that, right? So actually, because of this, the flux depends on one extra bit of information. So if I have a surface and when I talk about it, the flux of a vector field across that surface, I have to choose on that surface an orientation. This is a name for, I have to choose a unit normal at each point. For example, here I could have chosen the other one. So with this unit normal, the flux here will be positive. All right, so we're talking about going, so quick comment before I make the next definition. So we already talked about flux when we were in 2D, and then we would talk about flux across a curve. Here in 3D, we talk about flux across a surface. So the idea is that the notion of flux to have flux, we have to have a vector field and some sort of wall that divides space in two, right? So a curve wouldn't divide space in two in 3D, but it does in 2D. So if I were, say, in 10 dimensions, we would be computing flux of a vector field across 9-dimensional hypersurface. Okay, so with that remark out of the way, let's be a little bit more precise here. So here's our definition for orientation. So an orientation of a surface S is a continuous choice of unit normal vectors. The surface S is a continuous choice okay, the surface doesn't look good here, is a continuous choice of unit normal vectors on S. On S. Right, so we're talking about, so let me go back to my usual surface. Here's the peanut shape, my favorite generic surface. And here's an exact identical copy of that peanut shape. Right, so for each point of this peanut shape, there are two, so there is only one normal direction. So if I choose the length of a vector with that direction, there is only, there are two normal directions, this one or the other one. And if I choose the length to be 1, there's only two normal vectors, this guy, this unit normal, and this other one here, which points down. Right, and for each point on the surface, I have all these normals. So here, if I start choosing this normal over here instead of the one that points down, as I move, if the choice is continuous as I get to this other point, I have to be on this. I have to choose this one rather than the other one, right? So if my surface is connected, there is a single choice of orientation. Right, so for all points on the surface, you end up choosing a normal. Okay, this picture is probably the worst picture I've seen. The picture in the notes is a little bit better, but the point is that either you choose the normal where either you choose the normals that point up or you choose the normals that point down. So in effect, this choice here is the orientation. So in effect, what you're doing is choosing one of the sides of the surface, right? So either this the upside or the down or the side you get by looking from the surface down up in this example. So I'll show you later when we talk about how we actually compute the integrals in Flux. I'll show you how to express n in terms of a parameterization. But let's hold off that for now. Here's another important definition. So not all surfaces. This is more academic. In practice, surfaces. You take a surface in your hands. It usually has two sides. It'll almost surely have two sides, but I should tell you that not all surfaces have two sides. So this notion of orientation, this choice of orientation is only possible on surfaces that have two sides, and not all surfaces have two sides. So let me just define here a word. So a surface is orientable if it has two sides. Right, so let me give you the canonical example of a non-orientable surface. So the Mobius strip, let me draw it for you. So here's the Mobius strip. Looks like this. Oh, actually, yeah, it's going to be... looks like this. Okay, so this shape, so the Mobius strip, which I just drew, is not orientable. It does not have two sides. Let's talk about this for a second. So first, let me make sure that we all understand what shape I'm talking about. So here on the right, I'll just explain how we get this shape. So first we start with you use scissors and glue, or actually just glue. So you start with a little rectangle of paper, and then you twist it. So let me twist it like this. So here I twisted it, and then I am going to get this piece and glue it this side. Okay, let me maybe do it in two steps. So the next step is to start, is to do this. Oops. And then you just start, just choose a point over here and bend a little bit like that. And then at the end, you just glue these opposite sides, just as they match, they overlap, let them overlap a little bit and glue them, and then you get the Mobius strip. All right, let's understand why the Mobius strip does not have two sides. So here's how we're going to go about this. We're going to use some imaginary paint. We're going to have red paint and blue paint, and I'm going to set aside the blue paint and start painting one side of the strip red. Once I'm done with that side, I'm going to get my blue bucket and start painting the Mobius strip blue. It turns out that once I'm done with it, there won't be anything to paint blue. So I think it'll be clear what I mean when I say that the Mobius strip has a single side. So let's do it. So I take my red paint and start painting here. This side of the back of the strip, which is facing us, right? There's the other side here on the back. Just let's start painting this side of the back of the strip that's facing us, red. And then once we get to this fold here on the right, you start painting the same. You continue painting, but this time you see that you're painting the part of the paper that's facing, the computer rather than facing you. Until you get to this twist, and then you revert back to painting the part of the strip that's visible to us, and then you go back to painting the back. Oh, but here's an interesting thing. Now I'm painting the back of a part that I had previously painted red, and when I get to the turn here, I start painting the front, the part that's visible to us in red. until I get to the twist and get back to painting the part that's not visible to us. And then I go back to painting where it originally started painting, and then suddenly, both quote unquote sides of the surface are painted red. Actually, there's a single side, and that one side is all red. So what I'm saying, so if going back to orientations and normal vectors and flux, so we're not going to be talking about flux across a surface like the Mobius strip, which has a single side. We will only talk about flux across surfaces which have two sides. Right, I would get into difficulties if I have to decide between this, if I wanted to do a continuous choice of normal vectors, and at some point, because at some point I would come back if I kept doing a normal choice, and that the continuity would tell me would contradict my choice. It would say that either the normal has to be this, but also has to be the other one. So we would be in bad shape. All right, so orientations. So most ordinary surfaces are orientable. These things, or non-orientable surfaces, exist, especially in the mathematician's imagination. But we won't have to worry about them. All right, so let me get this picture over here back. Right, we're gonna go back to talking about it. Let me just tell you what flux is with this definition, this terminology out of the way. So the flux of the vector field F across the oriented surface S is by definition the double integral over that surface of a certain function with respect to ds. Right? And here I'm going to tell you a function. It's a function I'm going to build out of the vector field and the normal. It's a very easy way to build a function out of two vectors. You just do two vectors, just take their dot product. Right? So F is a vector field, N is a family of normal vectors. So for each point on the surface, I take the dot product of F with N. This gives me a number, and then I multiply. I mean, if you think in terms of Riemann sums, you multiply that number by the area of a little piece of the surface, add over the surface, that gives you the flux. So this is our definition. This is the main topic of today. So let me note that in the homework, in the book, online, you'll often see ds written with an arrow on top of it instead of n times ds. So the idea is that ds with an arrow on top of it is an infinitesimal vector, really, really small vector. The direction is the unit normal to the surface at each point of the surface, and the length is just the area of a little piece, area of a little piece of the surface around that point. So later, so very soon I'll tell you how to set up these things in practice. But before we do a computation that we don't really understand, let's without an interpretation for it, let me just quickly tell you the interpretation, because we've already talked about flux, and here this time it's going to be the same. So the interpretation is I'm going to draw from our experience in let's look at what happens in the situation where F is the velocity field of a fluid. So here let's look at the surface sideways, and we have our normal vector, our unit normal vector N, right? It's perpendicular to the surface, and we have our vector field, or velocity field of the fluid F. So F is the velocity, is fluid velocity. Okay, and we want to understand, also we have, let's say we have a little piece of, a little area of the surface, so delta S, and we want to understand these things, these numbers we're adding together in the integral. So we want to understand f dot product the unit normal times ds. Here s is uppercase because we're talking about, the convention is we're talking about the area in the surface. We use an uppercase s. If we were talking about length in a curve, we would use a lowercase s. Okay, so we want to understand this number. And here's the interpretation. So I'm going to draw, it's going to be the volume of fluid. This here, it's going to be the volume of fluid that crosses delta S in 1 unit of time. Right, so here, so let's say, let me just draw that volume of fluid that we're talking about. So I'm saying that this number, these numbers that I'm adding in the integral, they give me the volume of this tower of fluid over here. It's the amount of fluid that crosses delta S, the volume of fluid that crosses delta S in 1 unit of time. And here's why. So if, let's say the velocity in a linear, so the speed is 10 miles per hour and you wait for 1 hour, then if the speed is constant or if the hour is really short, I mean, if the speed is not changing in 1 hour very noticeably, then the distance will be 10 miles. If you go at 10 miles per hour and for 1 hour, you just move 10 miles. Similarly, if you just wait a little bit of time, if you wait 1 unit of time, then this amount of fluid will have crossed, the fluid was here, will have ended up there after 1 unit of time. And similarly here, and similarly for all of them. And some like as this point moves here, some fluid particles that were behind it, just occupy the other points, and then you get this little tower. And the volume of this tower is the area of the base times the height. Now, just a moment, please. So so f dot n, so this part over here is, if this is cosine theta, this is just the length of f times the length of the unit normal, that's just cosine theta. And this is actually just the height of the tower of fluid. So multiplying the height of this tower, f cosine theta, times by the area of the base, and so I get the volume of fluid. A fluid through this little piece of surface, so through delta S per unit time, in 1 unit of time. Right, so it's you could say it's going to be some number of cubic feet per second, right? That's an amount. So this integral is going to give you a number that's going to be, if f is the velocity field of a fluid, the result of the integral is going to be some number of cubic feet per unit time per second, or some other. I mean, if you're using feet and seconds to measure distance and time respectively. Okay, so this is the interpretation. I'd like to now show you how to compute this integral. So let's do that. So we're going to, so the trick here is going to be, so we're going to describe, so I have to tell you how to set this up assuming that we have a parameterization of the surface. So the key step is understanding ds. So let's do that. So if we have, so here we have a nice surface, and here is our normal vector field. On this surface, and we also have a parameterization. So S has this parameterization R in terms of 2 parameters U and V, right? And then I get some, so the parameterization just gives me formulas for X, Y, and Z on the surface in terms of U and V. If you give me points U and V, I get a point X, Y, Z on the surface. Okay, so the unit normal. So we're interested in ds, right? That's the unit normal times ds without the arrow. Vector ds has these two pieces. So first, what's the unit normal? It's going to be, okay, so how can we build a unit normal vector field here? So we've talked about normals on surfaces before, right? We said that if I just fix one of the variables and let the other one vary, I get a curve on the surface. So if I fix v and let u vary, I get a curve on the surface. If I differentiate with respect to u, I get the velocity of that curve, which is a tangent vector to the surface. Here, if I fix the other variable, I get a different curve and a different velocity. So if I take the cross product of those two, I get a normal vector to my surface. Now this normal vector is not necessarily a unit normal vector, so let me just divide it by its length, and then that gives me a unit normal vector to the surface. And we're almost there, right? So we still, the issue is that when I play this game, depending on what I call u and what I call v, I may end up doing this cross product differently, and then the result changes by a sign. So I may either, when I do this cross product, I may get the normal vector I chose, the one that I said this is the orientation. This is the orientation of my surface. This choice up here is the orientation, or I could have gotten the other one, which is not the normal I chose when I fixed the orientation. So, but still, this formula gets us pretty close. So on every single homework problem or in every single calculation, we have to decide. We do this to find the normal. We just do this cross product, and then we ask ourselves, okay, does this give me the normal the problem asks for? Is this, for example, here I would describe this normal with words saying this is the upward orientation. Would I describe this cross product as the upward normal vector or not? Or would I say this is the downward, in which case I should use a minus? All right, so n is going to be plus or minus this, and then the plus or minus you decide every time you do a problem. ds we already worked out when we were integrating functions, so that's just the length of the cross product times du dv. So whenever you see a ds and you're computing the integral using a parameterization, you can just replace ds by this. And so you see that ds with an arrow on top of it, that's the vector, the unit normal times ds without the arrow, is just, when you multiply these two, the length cancels and you're left with less work than than before, right? So ds with an arrow on top of it is easier to compute than without, because it's just plus or minus the cross product times du dv. This is another important fact. Right before we were doing things like integrals which required ds without the arrow. When we were integrating functions, we would integrate ds without the arrow, and then we would have to compute the cross product and then take its length. But now there is no need to take the length. Just computing the cross product is enough. So let me now show you how this looks in practice. So here's a good example. I'm going to take for my vector field the vector field yxz. So f is yxz, right? The first component is y, second is x, third is z. And I'm going to say my surface is a piece of this upside down paraboloid. It's the piece of the upside down paraboloid with equation z equals 1 minus x squared minus y squared, that lies above the xy plane. Right, so S is this surface over here with these equations. So I'm looking at the part of this upside down paraboloid that lies above the xy plane, and okay, let me just, sorry. And I'm going to, so here I have two of the three ingredients I need to compute the integral. I have the vector field, I have the surface. I still need to choose an orientation of the surface, right? It's a simple choice. Here I'm going to make the, say we're interested in the upward orientation. All right, so here in red you see I'm using the upward unit normal throughout the surface. Okay, so this is our situation. So let's get busy. Let's calculate this stuff. So here, this surface is really a part of a graph. So z equals some function of x and y. That describes my surface. And we're looking at the part of this graph over the unit disk, right? Over this disk over here. And this disk lies on the xy plane. Let's see if I can draw this stuff. This disk lies on the xy plane, and if I say that z is 0, so on D, on the xy plane, z is 0, and so x squared plus y squared is 1, so this disk has radius 1. So for example, this point here is 1, 0, 0, and this point is 0, 1, 0. The point being that the projection, so S is the graph of this function over here over the disk of radius 1. Right. So how are we going to parameterize a graph? Well, we've done this a couple of times. So to describe point on a graph in terms of two numbers, if I have only two numbers to describe the three coordinates of a point on a graph, will just tell you the x and y coordinates, and then you can figure out the z by just from knowing what function we're talking about. So the parameterization is x, y, and then, so x is x, y is y, and then z is 1 minus x squared minus y squared. That's our function. And then we have to do the partials, the cross product of these partials. Right, that's important for a calculation. So we've done this a couple of times. Let me just do it. Otherwise, you guys won't. I mean, I don't want to stretch your memory. Okay, so let's do this cross product. The x partials here are 1, 0, and the x partial of this part over here, that's minus 2x. Oops. The y partial is, the y partials of the three components are 0, 1, and minus 2y. So if I work this out, I get I times 0 minus 2x, minus 2x, that's 2x. And then j component is minus 2x times 0 minus 2y, that's just 2y. And then finally, the k component is 1 minus 0, that's 1. Okay, so there is our cross product. Now we're going to, so here's something we're going to need. We're going to need ds with an arrow on top of it, and that's plus or minus r sub x cross r sub y dx dy. Right. So that's, again, in this, I mean, we just worked out what the cross product is. That's 2x, 2y, 1. And remember, I should remind you, so now we have to decide the sign. Remember that ds is the unit normal times the area element. So the area element on the surface is a positive infinitesimal, if that makes sense. And here, the unit normal, we are interested in the unit normal that points up. Right, you see here there's this unit normal and there's the other one that points down. And you can tell them apart on this example. When I say one points up and the other points down, is that if I look at if I look at the z component of this vector, I'm going to say, so the way it's different, the way this vector is different from that one is that this one has the z component is positive for this one, and for the other one it's negative. Right? So n here has a positive z component. So n times ds should have a positive z component, and the way I can do that is by choosing. So if I want the z component to be positive here, I should use the plus sign. So let me just, annotate, write down that choice. Okay, so we have r, and finally we should express our vector field. So to compute the integral, we have to express our vector field in terms of x and y, right? So f of xy, f of r of xy, right here I'm expressing the vector field in terms of the two parameters. That's, the parameters are y and x, x and y, so I get y, x, and then z, but z on the surfaces I wrote over here is this. So y, x, z. So that's y, x, and then 1 minus x squared minus y squared. Okay, so we're ready to compute the flux. That's the double integral over this surface of the vector field times ds. That is the same as the that's equal to the double integral over the disk of radius 1. And then here we're integrating this vector field y, x, 1 minus x squared minus y squared multiplied, so here's a dot product, with ds multiplied by, so the ds was with an arrow on top of it. Oh, excuse me, I should have completed this. So multiplied by this, right? So we're using the plus sign, so that's just 2x, 2y, multiplied by plus this thing over here, times dx dy. So here we're doing the double integral over the disk of 2, so here do the dot product, 2xy plus another 2xy, that's this product, this, and then plus these two things. So the product of those two things is this. Okay, and now, well, okay, this is just an ordinary, we're integrating a reasonable function over a region of the xy plane. That's something, that's fine. That's something we can do. Let's just do it. Or at least let me just give you an idea how we do this. I've been known to skip less than inspiring calculations from time to time. So here, if to do this, we should change coordinates to polars. We're working over the disk of radius 1. So theta goes from 0 to 2 pi, r from 0 to 1. And then we have 4 times x times y, that's r squared cosine theta sine theta, plus 1 minus r squared. And then dx dy, that's r dr d theta. And I guess this is where I'll leave you guys, so you can, if you just work this out, I mean the integral, so sine is basically, okay, so cosine, actually it's better to bring this to the front. So cosine is the derivative of sine, so this part over here integrates with respect to theta to sine squared over 2, evaluated between 0 and 2 pi, that'll die out. And then this other part over here just gives us 2 pi over 2. Right, and in the exam, please always box your answer. Right, we're going to get some number out of the integral with respect to r, and we'll in the end multiply that number by 2 pi, and we'll get this. Okay, so this is how we set up flux surface integrals. And I think this is a good point to stop today. When we talk about the divergence theorem, I want we all to be feeling very fresh and ready to appreciate how beautiful it is. Okay, so thanks for listening, and I'll see you guys next time.